Welcome to The Explainer. Today, we're diving into the absolute brilliance of the human brain, specifically the incredible mathematically precise hacks it uses to get around some pretty severe biological bottlenecks. We're going to break down some fascinating recent neuroscientific research and information theoretic analyses. Basically, we're going to figure out exactly how our minds optimize for speed, memory capacity, and ultimately survival, often entirely beneath our conscious awareness.
So let's just jump right in. We all kind of like to think we're multitasking masters, right? It's incredibly common to believe that we can consciously focus on multiple complex tasks at exactly the same time. But well, neuroscience paints a very different picture. True, deliberate multitasking is, biologically speaking, essentially a total myth. And it all comes down to the strict, hardwired limits of our minds. Section 1, the prefrontal traffic jam, or as researchers call it, the frontal bottleneck. To understand why multitasking is a myth, we have to look at the prefrontal cortex, or PFC. Think of this as your brain's command center for flexible thinking and conscious decision-making. The problem? It suffers from a severe bottleneck. It can generally handle only one active decision at a time. This is exactly why trying to deliberately juggle two complex things at once feels like a literal traffic jam in your head. The tasks are actively interfering with one another because they are fighting tooth and nail for the exact same, singular processing lane. Section 2, rewiring for autopilot and the perception action loop. So you might be wondering, how do we ever get good at anything, like, say, driving a car or playing an instrument, without constantly crashing our mental computer? The answer is repetition, but we're talking about repetition at a massive scale. Researchers actually tracked participants who practiced a visual categorization task, basically sorting morphed car images into categories, over 30,000 times. Over 30,000! And what they found was wild. Participants didn't just get subjectively better at it, that sheer volume of repetition physically changed how their brains routed the information. Let's break down how this happens across the stages of learning. Initially, your prefrontal cortex has to step in and consciously guide your visual areas to make a decision. It's slow. But with enough practice, your brain's vision center, specifically an area called the ventral occipito-temporal cortex, or VOTC, learns to make that categorization entirely independently. Eventually, the VOTC literally unplugs from the prefrontal cortex and forms direct, super strong connections straight to your motor areas. This creates a perception action loop. You see a stimulus, and you physically react, skipping that slow, deliberate thinking stage entirely.
Now, what's really fascinating here is the ultimate trade-off we're making. When you use deliberate PFC thinking, it's highly flexible. You can adapt to new rules on the fly. But it's slow, it requires a ton of effort, and it's absolutely terrible at multitasking. On the flip side, that newly rewired VOTC's motor loop, it's lightning fast, it takes minimal conscious effort, completely bypassing that frontal bottleneck so you can actually multitask. The catch, though, is that it's extremely rigid. If the rules of the game suddenly change, this automated autopilot severely struggles to adapt.
Section 3, memory bandwidth and noise, focusing on visual working memory.
Bypassing the frontal bottleneck is an amazing trick, but it's just one way the brain optimizes itself. The second major hardware limit we face is our visual working memory. This is your ability to rapidly store and access task-relevant visual information. But, as we'll see, it is severely constrained. Think about the journey of a visual signal. You take in an information source, but it's almost immediately corrupted by sensory noise. It then enters your working memory system, where an optimal encoder and decoder try to process it. Ultimately, what you remember is not a perfect 4K photograph. It is a noise-corrupted reconstruction of the original signal. To really grasp this constraint, science now models memory using rate distortion theory. This basically treats the human brain like a communication channel. So memory capacity isn't measured in a number of objects, it's actually measured in bits of information. Think of your memory capacity as a limited tank of water that you have to distribute across a garden. If you try to water way too many plants, none of them get enough water to thrive. Similarly, if you encode too many items in your mind, the noise increases and your memory precision just plummets. And this brings us to a hard, undeniable mathematical limit. When you map the theoretical minimum information rate required for a certain level of accuracy, you get a rate distortion curve. Below that curve is an infeasible region, and I mean that literally. It represents a mathematical impossibility. No physical system, whether it's biological, like our brains, or artificial, like a computer, can operate in that zone. You absolutely cannot exceed this performance bound without having sufficient capacity.
So, the really crucial takeaway here is this. When you find your memory failing or getting fuzzy in complex situations, it isn't necessarily a failure of your personal focus or a lack of effort. The performance degradation you're experiencing is a mathematical necessity of your limited neural bandwidth. When your capacity runs low, noise and corruption inevitably rise. It's just math. Moving right along to Section 4, the flexible encoding model and how we handle memory allocation. This whole capacity limit raises a really fascinating question. How exactly does your brain decide to distribute its limited bits? Well, for a long time, scientists argued between two main ideas. The discrete slot model suggested we have about 3 to 4 fixed slots in our memory, kind of like a parking lot, and accuracy stays high until those specific slots are completely full. Alternatively, the continuous resource model argued we just have one single pool of brain power spread across everything we see. Actually, though, both theories fall short. The slot model fails to explain why our precision still drops even when we're only looking at 2 items, and the continuous model totally fails to account for how our changing environment impacts our memory performance. So, what's the actual answer? The current mathematical winner, derived from ideal observer analysis, is the flexible encoding model. It suggests our brains are incredibly dynamic. Instead of using fixed slots, items in our environment are probabilistically selected for encoding based on the specific situation. There is massive, massive variability from moment to moment. Sometimes your brain decides to remember a whole bunch of items with very low precision. Other times, it dedicates all its available bits to remembering just a couple of items perfectly. It calculates this trade-off constantly, entirely on the fly. And this flexible approach elegantly illustrates why adaptability is so absolutely vital for us. When your environment has high variance, meaning things are complex, unpredictable, and vastly different from one another, your fixed memory capacity has to stretch much, much wider. As the math dictates, the data clearly shows that when this variance increases, your memory precision fundamentally drops. And finally, Section 5, built-in biases and safeguards. Basically, our brain's safety nets. Because our brains are constantly operating right on the razor's edge of these absolute mathematical limits, evolution has given us a built-in suite of safety nets. Remember how we said working memory is essentially a noisy channel? Well, to deal with that, your brain acts as an optimal Bayesian decoder. To prevent catastrophic memory failures, it combines the noisy limited data you just took in with your prior knowledge, basically the statistical averages of what it expects to see based on your past experiences. As a result, your brain inadvertently biases your memories toward the average. It actually tweaks your recollection to be closer to the mean because, mathematically speaking, that is the safest way to minimize overall error when you're running out of mental capacity. Furthermore, when uncertainty gets too high and the noise is just overwhelming, the brain pulls the emergency brake. Research into the hippocampus reveals a mechanism called defensive inhibition. Its entire job is exactly this: to inhibit your ongoing behavior to prevent impulsive, disadvantageous choices. You know when you experience a cognitive freeze? When your mind just goes totally blank in a high-stress, complex situation? That is not a failure. It's actually a neurological safeguard, locking down your system to stop you from making chaotic, probabilistic guesses that could end up harming you. We've seen how our brains literally, physically rewire themselves to bypass the prefrontal traffic jam, and how they execute incredibly complex, instantaneous mathematical equations just to distribute our limited memory bits. It begs an absolutely incredible question to end on. If your most flawless, rapid skills require completely bypassing your conscious thought, and if your memory is quietly tweaking your reality to fit statistical averages to keep you safe, what else in your daily life is your autopilot quietly controlling without you ever even knowing? Thank you so much for joining me for this explainer. Keep questioning everything you think you know about your own mind.